Last day, we have seen the basics of the physical parameter momentum. Today, what we shall do, with the help of that basic knowledge of momentum, we shall discuss something about motion of a rocket. Now, of course, we are not immediately going to discuss space science or astronomy, just how, just the equation we shall derive about the uh, velocity of a rocket at any point of time. And for that equation, we shall need the knowledge of momentum that we have done last time. Now, we all know today, everybody knows how a rocket looks like. This is a, let us write it in vertical direction. And there is a exhaust gas. And rocket moves upward. Now, a few basic considerations we write down first. Let us uh, say initial mass of a rocket plus fuel m. Then let us say rate of fuel discharge, or fuel will be actually discharged in terms of gas. Fuel discharge the fuel discharge, say, equal to R, right? And also one more thing we write, these are the initial condition, initial assumptions. Let us say velocity of discharge gas respect to now let us say at any instant of time, say at any instant of time t, at any instant of time t, the mass of rocket plus fuel is m. At any instant, the mass is m and velocity is equal to v. At any instant. Now, rocket velocity is v and rocket mass is m at any instant. Of course, initially, the mass was m0. Now, during its upward motion at any instant, its velocity v and mass m. And discharge velocity is u. And what is the discharge velocity of u with respect to the rocket? So, discharge velocity, so we also write here discharge velocity respect to r equal to, of course, V minus U. Right? Now, at this moment, at this moment, at this moment, at this, what is the momentum of the rocket? Momentum of the rocket is mv. Momentum term of rocket equal to mv. Now consider a small interval of time del t. Consider a small interval of time del t. And during this interval, the velocity will increase during this interval, or after this interval, you can say interval, velocity increases as del v. And mass of the rocket will decrease because some fuel has been spent. Mass is 2. Mass decreases to m minus del m. During this small time of interval, del t. And if del m is the decrease of the mass, then del m is the amount of fuel which has been discharged. So we can write mass of the discharge, mass of the discharge is equal to del m, and velocity of the discharge, velocity of the discharge is already given. We have done it earlier, is v minus u. Then what is the initial momentum that we have seen earlier? Initial momentum is mv. And final momentum has two components. One component is so we can write here like this. Initial momentum mv will be equal to final momentum of the rocket, final momentum of rocket plus final momentum of the discharge. Final momentum of discharge. There is no doubt in this. This is by the law of conservation of the momentum. Now, initial momentum is mv. And what is the final momentum of the rocket? Final mass of the rocket is capital M minus del M. Capital M minus del. And final velocity of the rocket is plus del V. V plus del V. Plus final momentum of the discharge. Mass of the discharge is del M and velocity of the discharge is yes, U. Clear? Now this is equal to, just keep on multiplying them. First is mv plus m del v, or we should always write del v first, del v m, then minus del mv minus del mv, then minus del m del v, del m del v, then plus del mv plus del mv, then minus del mu. L, we have been writing capital M minus del mu. Right? Now here, this term del into del is ignored because you have done it in differential calculus or any applied mathematics part. Then when you have two multiplication of two infinitesimal small elements, you can ignore this. And ignore this. Now this MB and this MB gets cancelled. Then we have a del MV minus del MV here plus del MV here. This also gets cancelled. So what we are left with is del Vm is equal to minus del mu, or del Vm will be equal to del mu, right? So what we are left with is del Vm, or we write m del V is equal to this term. So these are the only two terms here which are left in the equation. Is equal to del m E. From here we get del V is equal to del m u by capital M, or you can write u by capital M. From here we divide both sides by del t. By del t is equal to del m by del t, del m by del t multiplied by u by m. Right? Now, this is equal to what is del m by del t? Del m by del t is equal to R. We write here since del M by del T, that means the rate of fall of mass of the rocket is actually the R, the rate of fuel discharge. The rate of fuel discharge. The rate of discharge. So del M by del T we replace by R. So it is equal to R U by capital M. So whole equation becomes very simple. Del V is equal to del V del T. Del V del T is equal to R U by M. This becomes a very simple equation. Now we shall use the method of integration to find out the velocity V. Now, since we have got this, then what we can write when del T is very, very small. From here, you have done it in differential equation. So, in differential, you can write dV R U by M. R U by M. Now, what is M? What is M? M, which is actually the mass at time t, is actually the mass at the zero time m0 minus rate of discharge into the time elapsed which has come. So m is equal to m0 minus rt. So we can write dp dt is equal to dp dt is equal to ru divided by m0 minus rt. It is equal to m0 minus rt. From here, we can find out the value of velocity v at the time of t. How do we find out? Just by integration over time 0 to t, and we have to integrate ru divided by m0 minus r dt. Mind it, here r is a constant, u is a constant, m0 is a constant, only t is the variable. So here we take records of the replacement. Take records of the replacement like this. We do one thing. You have done it in your mathematics class, but I'll do it here once again. Say m0 minus rt is equal to x. Consider that so that dx differentiated both sides, dx is equal to minus r dt. Minus r dt. That means dt is equal to minus 1 by r minus 1 by r dx. This is one thing. Second thing, what you have to do, you have to also find out the limit. We found out the limits when t equal to 0, because here it was integration over t and limit was 0. When t equal to 0, from this equation we find t equal to, when t equal to 0, then x equal to m0, and when t is equal to t, then x equal to m0 minus rt. So if you just use this replacement, then what the equation becomes? D becomes integration of RU, integration of RU, and dt is replaced by minus 1 by r dx, minus 1 by r dx, and this function considered m0 minus rt equal to x, so this becomes 1 by x, and the limits are t equal to 0, x equal to m0, and this is m0 minus rt. I think you have understood this part, that this is a part of mathematics actually, and this is dx. So this is equal to this ru, these are all constants, so we have here minus u. We have here minus, this r gets cancelled, we have here minus u, and integration of 1 by x is natural log of x. And limit is from m0 to m minus rt. Right? So this is equal to minus u outside. What we have inside? Natural log of m0 minus rt minus natural log of m0. Now, if you bring the negative sign outside, a negative sign inside, this is equal to u. And inside you will have natural log of m0 minus natural log of m0 minus rt. This is equal to, by the formula of natural log, this is equal to u multiplied by natural log of m0 divided by m0 minus r. So this is the, so the velocity v of the rocket at time t is given by v equal to u. Is u, remember, u is the velocity of the discharge with respect to the rocket. That you have to always remember. That's subordinate clause, with respect to the rocket. U multiplied by natural log of m0 is the initial mass of the rocket before it blasted off, divided by m0 minus r. R is the rate of discharge, t is the time. So with this formula, you can always determine velocity of the rocket at any instant of time t. Right? So this is so far as the rocket, etc. is concerned. Next, we shall see the lesson of in the chapter of momentum, we shall see the lesson of collisions. There are various types of when two bodies collide. then what happens so far as their momentum is concerned?